Yeah, and the title of the talk is followed by the Gaussian curvature and its power. So this welcome for
Thank you very much. It's my great pleasure to be in Taiwan. I apologize. Some people here may heard most of my talk, particularly this one. But I hope I can show you something a little bit new. Right. So the topic is mostly a partial differential equation. So it's has geometrical flavor because it's coming out of study of the convex bodies, evolving by this thing called Gauss curvature, right? How this works? Just okay. So I guess probably many people in Taiwan didn't hear this talk, and many of my friends also probably didn't hear my talk also. I just give you a little bit of overview about what it's about and what we contributed, and also some recent progresses. So, right. I'm considering a bounded convex domain, and then its boundary is a hypersurface, right? So I looked at the embeddings of the hypersurface. And there's a Gauss curvature. I did not know to be the normal of the hypersurface, and the flow is like this. So it's pretty simple. The flow was proposed by Faraday many years ago. So he observes this flow can be used to model the wheeling process of storms on a beach. So of course. You kind of can think about it. It's kind of natural model because when the wave carries the storm to hit the bank, the sharp sides got hit more, assuming the normal is evenly distributed because there's more normal there. There's more chance probabilities to get hit. So that's the motivation of the flow. And right, I mean, we mainly use this one particular parametrization, parameterized by the inverse of the Gauss map, because the hypersurface is strictly convex. The Gauss map is a diffeomorphism from the hypersurface to the sphere. So we could use the inverse to parameterize the hypersurface. This kind of gives you canonical parameterizations. This was originally used by Ben Andrews in his thesis. So he used this parameterization to study hypersurface flow, and in many cases greatly simplified the picture. So particularly he gave a proof of Huysken's theorem on convex hypersurface flow by mean curvature, right? So using these parameterizations, he could greatly generalize the theorems to all the homogeneous degree 1 speed functions with certain structure assumptions. So that's the parameterization we use, right? So really the flow is looks like this. If you really care about the geometric shapes, because the some simple computations tells you the embedding can be recovered from the supporter function in this way. So if you know the supporter function is a function on the unit sphere. So it's gradient of the unit sphere. Taking gradient of that function on the unit sphere is giving you the tangential vector, and then there's a normal vector. X is being the normal, right? So the whole position can be recovered. Okay, so this equation and the previous equation only differs by something on the tangential directions. So if you don't care about tangential directions, you only need to study this PDE. And the second fundamental form can be also recovered from the supporter function. So that's the formula. So this is A is we view that as a symmetrical tensor You just take the hashing of the U on the sphere, and then there's an identity map. Well, basically just the metric of the sphere. So you add them together. So this is the inverse of one-guided map. So this is basically set up all was done by Ben Andrews in his thesis. So he used this Gauss map parameterizations to try to understand the hypersurface flows. Okay. So if you do that, then the PDE becomes a parabolic Monge-Champagne type of PDE. So if you replace the Gauss curvature by 1 over determinant of U identity plus the hashing of U, so that's the PDE. Okay. It's kind of like Ricci flow. So if you have potential, you can reduce the whole system into one equation. So that is what's happening here. Okay, so you want to study this PDE. It's a Monge-Champagne type of PDE. And of course, if you want to flow by a power of Gauss curvature, it's really just take k power of alpha. And we call it power of Gauss curvature flow, right? So for alpha equals to 1 over m plus 2, this is a very special flow. This flow was studied by many years ago by Ben Andrews again, because this k power of 1 over m plus 2 is so-called Eiffel normal. So it's related to Eiffel geometry. So Calabi studied this, the invariance of hypes in Eiffel geometry, mainly the invariance of the geometry under the Eiffel group transformations. So also the other power was proposed and studied in applied math. So people try to use this to model certain image process with different alpha. Okay. It's not just we want to do it mathematically. It also has application to understand different powers. Okay. From PDE point of view, also it's interesting to understand the powers because it shows different nonlinearity and singularity and degeneration. So for different power. So it affects the PDE. The known result is this flows hypersurface to a point. So this was proved for alpha equals to 1 by Cao Qichen, and for general alpha by Ben Chao in his thesis. So we assume we're going to, by translation, we're going to assume this point is to be origin from now, because that is inside all the intermediate bodies, this particular point. So the goal is to try to understand what is the asymptotic shape of the flow, right? So we do normalizations. So normalization is one way to do normalizations, to normalize the enclosed volume. So make sure the volume enclosed is 1. I mean, it's not 1, it's not changing. So we make sure the enclosed volume equals to volume of unit ball. That's all normalization. So to do that normalization, there's different ways to achieve that. One of them is just by scalings, right? By scale the convex body or scale the hypersurface. So that is the scaling. You kind of can imagine that's the right scaling because the volume shrinks to a point, it eventually becomes 0. So you have to scale the sense by blowing sense up, but the dimension should be the volume's 1 over m plus 1 dimension. So that's the right dimension. If you put that scaling in, you get this normalized flow. Okay. This is just a computation. So this normalized flow is going to preserve the enclosed volume. Okay, so, the volume is not changing. You do a little bit of computations, it shows. Also, by the way, which scale this is, right? Okay. So the method we try to study this is via a functional we call entropy functional. So this is a functional defined, it's a bit different from parameter entropy, right? So because it's defined only use the C0 quantities of the geometry. So you specify any points inside the body, you can define these so-called support functions. I mentioned support function previously. These two definitions are equivalent, right? You just look at the directions, and then you see how the furthest points you can move away, right? So it's kind of like you have a convex body. You pick up a point, and then you pick up the directions. Let's say this is the direction. You just keep moving in until it touches. So the distance to the hyperplane is a support function. That's the furthest you can get. If you stay inside, I mean, you pick up, you normalize a point. You put a 0, 0, 0 here. And okay, then you have this quantity. It depends on the point. It depends on your normalizations. The easiest one is alpha equals to 1 case. That's just the log of this support function. Support function is always positive if you pick up a point in the interior. So you take a log of it, you integrate on the sphere, and then you average out. So the other ones is just as alpha goes to 1, limits to it. So it's just different LP power of average. Take a log. Okay, so then the entropy is defined to be, we take soup among all the possible points you could choose. Okay. It's a bit similar to this Cody-Minicozzi entropy for mean-curvature flow. You have to take space-time maximum. Here we take soup for the points inside the convex body. So you can prove certain basic properties of it. So the basic property of it, there's some geometric meanings of this functional. Okay. So the geometric meanings, if right, I mean for alpha equals to 1, it's kind of easier to understand it. There's a geometric constructions in convex geometry. It's called a polar dual. So you give you a convex bodies, you can construct a dual of it. So that's a construction. Okay. So for instance, a dual of a ball, if you put the point in the center, it's a ball. But if the point is on the not center, it's going to be an ellipsoid. So there's a geometrical ways to construct the duals. So you look at the dual body, and then you look at the symmetric difference of the unit ball and the dual body. Okay, we normalize the body has volume same as the volume of the unit ball. Okay, you look at the symmetric differences. So then you put this weight. So this weight usually it's not integrable at the center, but the center got removed, right? So because I translated my dual body to the origin. So the origin is not inside the, how should I say that? I mean, this is a singular integral, but the singularity got removed. Okay, there's no singularities. So it's weighted volume with respect to this weight. That's what the entropy is. And for other ones, you could do the similar sense. There's some geometrical ways to understand what the entropy is. It's some singular integrals, weighted volumes of the dual. Okay, it's kind of like this f functionals of mean curvature is weighted of exponential functions, Gaussians. So, but here we weighted with this singular weight. So. It has some uses, these geometrical ways to look at the things. Because otherwise, it's you don't know why you consider this kind of quantities. Right? It has some geometric origins. also you can prove, okay, the maximum can be attained in the interior. And it's unique, and it can be uniquely characterized, the point. So the where the maximum is attained satisfies, this is Lagrangian equation, and you know it's a strictly, it's unique. There's a stabilities, right? So if you move away, it's always getting smaller. So for other points, the entropy is smaller. Okay, it's unique maximum. And then you also can prove it's always non-negative, because you have to somehow satisfy all these physical axioms of entropy quantities. So it has to be non-negative. Certain monotonicities later on. So also compares with the previous ones. So there is one for Gauss curvature flow involve C2 quantities. That was Ben Chow's entropy. He came up with this after Hamilton proved these entropy formulas for surfaces for Ricci flow. And Ben Chow came up with this k log k quantity integrations on the hypersurface, and he proved this quantity is monotone under the normalized flow for Gauss curvature flow. But that's harder to use. So any applications? I'm not sure. Probably just one or two. Probably Hamilton used it afterwards to derive something. But it's harder to use. So this entropy quantity we construct is always smaller than Ben Chow's. Okay. I don't think Ben ever proved that this quantity is non-negative. It follows from this all constructions, right? So because we show all is always non-negative, so therefore his is non-negative. His is bigger. And also this quantity was studied by Ben Andrews. He basically generalized Ben Chow's considerations to the alpha power. So basically it's similar to the C0 constructions, right? So it's just the LP norm of the Gauss curvature, and then you take log of it. So as alpha goes to 1, you converge to Ben Chow's quantity. Also, Ben Andrews proves the monotonicities of this too for the flow by power of alpha. Okay. So another important property is this quantity is monotone, not increasing along the flow. Okay. In fact, you prove it's very similar to Perelman's entropy or other sense, right? So because this is the supremum. So in the real proof is you don't really prove for the supremum. You prove for the one fixed reference point. So because you take soup, so the monotonicity follows there. So you kind of look backwards. So at some point t, you want to prove for previous t, this entropy is bigger. So how do you do that? Well, you at this particular point, you pick up the entropy point, and then you look at the entropy centered at that point, you look backwards. So it's increasing for that particular point. Therefore, the soup is going to be bigger at a previous time. It's very similar. Okay, and also we have similar non-collapsing estimates. So this entropy is quite important. If you can control it, you can do quite a bit. So you can get some geometric information out of it. Oops. Okay. So non-collapsing estimates. Okay. Maybe I show you the statement later on. But now I tell you some works has been done for this. So for two-dimensional cases, Ben Andrews proves this statement. It always converges to a round sphere. Okay, so he come up with very clever estimates. So the estimate is so-called it's a pinching estimate, right? But he proved for the non-scalar version pinching estimates. This is just for the flow before normalizations. Before normalizations, the difference between two principal curvatures controlled by a difference of the principal curvature of the initial term. So you know the whole thing shrinks to a point, and the Gauss curvature goes to zero. Goes to infinity. The volume goes to zero. If you scale everything back, so the scaled version of estimate basically tells you the difference of two principal curvatures is going to goes to zero. So the limit is wrong. That's how the proof goes. Okay. Well, they try to generalize this for different alpha. They work pretty hard on it. The algebra become a bit crazy for general alpha. So they worked on this. And there's a alpha equals to 1 over n cases. That's the case considered by Ben Chow again in his thesis. So he proved it converges to a round sphere using pretty much similar argument of Huysken. But as I mentioned, Ben Andrews proved a more general result for all the homogeneous degree 1 speed functions with certain structure conditions. Our result basically says the normalized flow converges to a soliton. And the soliton is strictly low bound on the Gauss curvature. You don't get degeneracy. And to prove this, we only need to establish estimates. Okay. So because Ben Andrews already set up the framework, he basically says, if you can prove uniform estimates, then the statement holds. So here the convergence is here also if you have uniform estimates, you only have sequential convergence, but the sequential convergence implies the convergence because there's Leon-Simons argument to get this uniqueness of limit. If your functional is analytic, depends on the underlying geometric structures. So there's a way to get uniform convergence if you can get one sequential convergence. So our main contribution is to prove a uniform C2 estimates for this flow independent of T. Okay. So how do we do that? That's a non-collapsing estimates. So the non-collapsing estimates is kind of like the first step. What it really tells you, the body is not going to collapse if the entropy has upper bound. Okay. So here there's some geometric quantities. One quantity is a rho minus. Rho minus is so-called inner radius. Inner radius is just the biggest radius of a ball you can fit in the convex body. Also, there's a W minus, which is so-called minimum width. So you put two parallel planes to try to fit in the convex bodies. You're rotating the parallel planes. So the narrowest, that's called width. Okay. Similarly, you also have rho plus. Rho plus is so-called autoradius. Autoradius is the smallest radius of a ball who can contain the convex body. You can from outside. And then also you have this W plus. W plus is the maximum of the width. So you take the parallel planes and rotating them. That's the biggest gap you fit in these convex bodies. So these two estimates basically tells you the body is not going to become very narrow and long. So it's if you have entropy controls. Okay, so that plays quite an important role in the argument. Okay, we need this. Then, because we know the entropy is monotone, non-increasing. So if you study a body, then the later body is not going to be getting worse. It's to your favor. Okay. the key is to get a C0 estimates. So we kind of abandoned the traditional strategy of doing all these curvature estimates by computing second fundamental forms and so on. Work with the U. Right. So the first estimate is the uniform low bound of this support functions with respect to the origin, which is the limit. So you have to rule out the possibilities as it go along, even though the origin lies inside all the bodies, but it can getting closer and closer to the boundary. You want to rule that out. So that's the first estimate you need to establish. How do we prove this? This is proved by three steps. The first step is so-called compactness argument. So it's kind of like studying Riemannian geometry. You have to get into metric spaces. Here you have to get into the convex body may not be smooth. So you even though we assume the initial ones is smooth and all the way flowing is smooth, to obtain the estimates you have to deal with non-smoothing case. So we look at the family of these convex bodies, which has certain non-collapsing properties. So it's not going to too narrow and the same, and stay in a fixed ball. So that's the one over rho. And then the statement is both the entropy and also the point depends continuously on the bodies. There's continuity properties. Okay. So if the two bodies are close enough, then the entropy are very close and the entropy points are very close. That's the first result. I mean the needed lemma. Second one is this is kind of important lemma. For any bodies inside my class, for gamma delta, so the entropy point to the boundaries always have a fixed distance. Okay, this is an important one because you have to prove this for non-smooth convex bodies. And then there's a stability lemma, which is number 6. So this basically just quantify the uniqueness of the maximum uniqueness of the entropy point. So basically it says if any other point is inside the interior, then we know its entropy is not maximum, but it's going to have a fixed amount of a drop, okay, estimated by the distance. So that's very important for us. Okay, once we have this, we can prove this C0 estimates. So the C0 estimates basically how it works, right? As I mentioned, as long as the point is inside the body, you have monotonicities. Okay, so the entropy monotonicity is really a consequence of that. So because the origin is a point inside all the bodies, so you could study. You could try to take a limit, right? For any t before infinity, you always have well-definedness of this quantity because it's in the interior, and then you can take a limit because you have monotonicities. So as t goes to infinity, it has a limit. So the estimate is kind of trivial, right? Because of monotonicities, so you're getting smaller, so it's always smaller than 0. But it's also if you take supremum here among all the points, it's getting smaller because you're minus something. Okay. So Right. Because you know the stabilities, right? Okay. So our previous estimate basically says the entropy point and origin, the distance is going to be controlled by the difference of the entropy at the entropy point and the entropy at the origin. Okay, but we know this guy goes to 0, hence this goes to 0. Okay, but on the other hand, we have this lemma. Let me show you. Okay, this lemma. This lemma tells you the entropy is always keep a fixed distance away from the boundary. So that tells us the origin is going to has a fixed distance away from the boundary. So hence the lower bound of the support functions. Okay, that's the argument. Okay. So after that, you have to control. You have to get it to C2 estimates. So C2 estimates involve 3 steps. The first one, we have to control the Gauss curvature from above. Second step is kind of a tricky step to control the Gauss curvature from below. Then once you have that, you can get the uniform C2 estimates. Okay. So the Gauss curvature here plays a role to prevent either become singular or become degenerate. So the first one is the upper bound. The upper bound is known before, so it has various proofs. Hamilton has a proof. I'm not sure he uses entropy monotonicity or not. He uses Ben-Child's entropy monotonicity. There's also original proof of tau. Also works for the upper bound of the Gauss curvature. Bang-Andrews also has a proof on this. So it's not a new estimate for the flow. So the new estimate is on the lower bound. Okay, because I think motivated by this, Hamilton at some point started to study the flow of Gauss curvature with flat side. So because he probably doesn't know, you could rule out such possibilities. You may somehow become 0 somewhere. So this can be ruled out. This part of argument is pretty tricky. So we also have 3 proofs now. The first one is kind of a tricky argument to use some sort of dyadic decompositions, right? So you chop the intervals into lots of many smaller and smaller intervals and try to do argument there using differential Harnack estimates. But now there's also estimates using maximum principle. I should watch out my time, right? I want you guys to be late for lunch or have afternoon activities. Maybe I just skip this argument. So if you find out right quantities and start to do maximum principles, you also can prove it. So the computation is mainly based on 2 evolution equations. One is how the k alpha power evolved under the linearized. So this operator is a linearized operator for the nonlinear flow. So you can linearize it. There's a linearized operator hit on k alpha. That's standard way to study this geometric PDEs. You just look at the linearized operators to see what happens. So that's one PDE. There's another PDE on the support functions. Then you cook up this product, log of the product. Then the maximum principles applies to this, gives you k's lower bound. Because you already have alpha's lower and upper bound. Okay. Also you have k's upper bound. So you play with the PDE, you can do it. So this is just showing how the proof works. Maybe I just skip it. Okay. So once we have that, we can have uniform CK estimates of the support functions. Okay. This is somewhat standard, but it's not exactly. I'm not sure it was written down. Maybe buried somewhere in Bang-Angel's paper, because he loaded several papers on the subject. Some of the papers very hard to sort out exactly what he proved, because he tried to write as most general as possible. So you look at the evolution equations on the inverse of the second fundamental forms. Okay, so it satisfies this PDE. Then you look at the trace of it. That's what I call sigma 1. So the trace satisfies certain PDEs. And then you try to use, I think here we used, then you try to use, okay, I should say sigma 1 is trace, sigma m is a determinant. So it's really the determinant of the inverse of second fundamental form. So this is sigma m is the inverse of the Gauss curvature. There's a sigma m minus 1. That's m minus 1 symmetrical functions of the inverse of the second fundamental forms. So you have these PDEs, and then you try to make use of it. So here you use some interpolation inequalities, some concavities, so-called Newton-Maclaurin inequalities between symmetrical functions. So you get at the maximum of the sigma 1, you get these estimates. So it's the key is here the power is slightly higher. So then you get a sigma 1 upper bound. So once you have sigma 1 upper bound, you're done with the business, because you know the trace bounded from above, determinant bounded from below. So the whole eigenvalue of the symmetrical tensor is controlled. Okay, then you have you're in business. You get all the estimates you want. So that explains the proof of the to the solitons. Okay. So then, of course, the question is, we want to understand what is the soliton? Can you classify them, right? The classification is pretty tricky business. We did some classifications, but essentially we only generalize the result of Faraday. Faraday originally proves modulo all the PDEs, okay, because the guy is really a convex geometer. He doesn't care about the PDE existence, regularities, any issues. So he just walk formally, in a sense. But he has lots of good insight, right? So he basically proves if it's centrally symmetric, then the soliton is a ball. Okay. Centrally symmetric meaning any point is inside this region, minus of that point is also inside that region. So right. So this we have a generalization of the result. Basically says for any alpha bigger than 1, if it's centrally symmetric, then the soliton is also a ball. Okay. The proof of this uses the so-called Blasik-Santano inequalities. So what is the inequality? The inequality basically says the volume times the dual is bounded from above if you minimize the dual, because dual is not unique. So if you are close to the boundary, the dual is huge. So you kind of minimize the product. So that's alpha invariant, and that bounded from above by the product of the balls. That's what the Blasik-Santano proves. So you use that, you can prove this result. Okay. As I said, the classification of the solitons was also studied quite a bit. For curve cases, was completely well understood. I mean, there's conjectures by Bang-Angels. Basically says for all the alpha bigger than 1 over m plus 2, the soliton should be sphere. And 1 over m plus 2 is a critical case. Okay. And for n equals to 1, he basically proves it. For m equals to 2, as I said, he proves for alpha equals to 1, and then later on generalized for other So did I make mistakes? I think the paper originally is half to 1, but somehow it's half to 2. So I think it's half to 1. This is the mistakes. And also, of course, Ben Chow proved for alpha equals to 1 over m, but he really basically proved the whole flow converges to sphere directly. There's also, later on, some people write down a proof just to classify the solitons directly. So there's an argument. It's very similar to Huysken's classification of solitons of mean convex, compact and mean convex, mean curvature flow solitons. It's very similar argument. His proof also works for other homogeneous degree 1 speed functions. Right, so Ben Angels also proved for alpha equals to 1 over m plus 2 cases. So the soliton cases for that particular one, in fact, was done by Calabi. So Calabi wrote a paper. That's where he studied this crazy C3 estimates. So he proved this using a C3 estimates. Okay, so more recently, there's 2 papers. One wrote by Chow and Daskalopoulos. They proved this for alpha between 1 over n and 1 plus 1 over m. Then Simon Brando joined the force, so they proved the whole region. And I show you, in fact, the proof is quite interesting because they come up with a new quantity. Because the new interesting features of this proof is the proof also works for alpha equals to 1 over m plus 2. It gives another proof of Calabi's theorem, okay, without getting into C3 estimates. So this quantity is kind of weird. Okay, it's combinations. We compute each one of them. So, but I mean, to put a combination, that's not by luck. Okay, so you have to have a good insight. I don't know where this expression comes from. So this is Gauss curvature's alpha power. So of course, as I showed you, we have to compute the sigma 1. That's trace of A. Okay, and this is just the position vector square. Okay, in fact, in our first paper, we computed aberration equations of this too, but we don't know how to use it. Turn out to be you have to use the combination of it. It's not just each one of them works. You have to put them together. So that's a pretty tricky part. I can give you a little bit. I have a little bit time insight on this. I guess probably you have to ask the authors to get a better understandings of it. But for the special cases of alpha equals to 1 over m plus 2. So the quantity is really just k 1 over m plus 2, then the trace of the inverse of second fundamental form, plus, because the coefficient turned out to be negative. So plus the position vector square. Okay, that's the quantity. So the quantity turned out to has geometrical meanings, but just by looking at it, you probably cannot see it. The geometrical meanings is the quantity becomes the summations of the radius of the ellipsoid for the ellipse. So if you have an ellipsoid, this quantity equals to the summation of all the radius. So it's not obvious, right? So I show you why. Basically, Calabi, before he did this, of course, he has to. Okay, I should say for the classification of m plus 2 cases, right? So the equation is this. So this is the soliton equation for alpha equals to 1 over m plus 2, the soliton equation. Even this on ellipsoid, why this holds, it's not completely obvious. I mean, I give you ellipsoid, you know how to compute its Gauss curvature, and why it's equals to u, right? Okay. So if you take an ellipsoid, so the boundary is, let's say, I use a BP, P equals to 1. So B is a positive symmetric matrix. This is the boundary, right? So this is the ellipse. This is omega. This is omega boundary on it. How do you compute its Gauss curvature? So you first of all compute its normal. So normal is pretty easy. So normal is BP over BP, because you just take derivatives of this, right? So if you change P on a curve, you get a BV P plus V plus BP V equals to 0. I'm sorry. V is not normal. V is just some tangential vectors. So you get BP V equals to 0 for any V tangential. For any points sitting inside the boundary. So you know that's the unit normal. So now from this, you know the second fundamental forms, right? So you can compute the second fundamental forms. So the second fundamental forms are just the d of nu act on any v is computed, right? So it's equals to bv over bp minus bp cubic, and then you have bp bv. So that's your that is your second fundamental form. Okay, you can write it as 1 over the BP B minus BV minus, let me see, I don't remember all the details. Calabi probably can do this in his head. I couldn't. Okay. Okay. Right. I'm sorry. So I put a B here. I put a B on top. V. Now it's BP, BV. P. So that's the second fundamental forms, right? So a priori, it's not very clear how do you compute the Gauss curvature. Maybe I spare that. I just try to show you how do you compute this quantity. Did I erase it? So the quantities that use is k 1 over n plus 2 trace of the inverse of second fundamental form minus x squared plus x squared. So that's the quantity. So how do you compute this? Even for ellipsoid, I made a claim this equals to the sum of the radius. Okay, the computation is like this. Okay, so if you let this equals to W, the first step is try to find out what is the what is the inverse of second fundamental forms? Because you already know this is second fundamental form for any V is tangential. So you want to find out what is the inverse. Okay, writing in terms of a B. Okay, so it's very easy to see. You can do B inverse of that equals to V minus BP BV divided by BB squared into P. So if you want to do inversion formulas, you have to resolve this because this is V. You want to write it in terms of W. Right? So what are you going to do to get a W? Well, you try to inner product both sides with with the normal. So take inner product with the normal. If you do that, on one hand side you have B inverse BP W, then the normal. On the other hand side, because V is tangential, it's gone. So it's going to be minus BP BV divided by BP square. And then you have P BP divided by BP. So, but this is equals to 1, right? So you get rid of it. So you figure out what is this in terms of W by this computations. So you have inversion formulas. Once you have inversion formulas, I can show you what is the inversion formulas. The inversion formula is the V. So basically, you can write out what is the inverse of the second fundamental forms for the ellipsoid case, which is BP B inverse W minus WP and P. So that is the inversion formulas. Okay, from here you can compute what is the trace A. Because you know the inverse, so you can compute the trace of inverse. So trace of inverse looks like this. So that's the trace of inverse. So from here you can get this quantity now equals to the sum. So this quantity turns out to be equals to the trace of B inverse. So that's the sum of the radius of. So my x is really just P. Okay? So x is the point of the position vectors. So to get this, we have to use the Sutherland formulas. K1 of m plus 2 equals to u. This holds on the. So okay. This is just the position, and the times the normal. So equals to 1 over BP. So you have to use this equations, plug into that to compute it. So hopefully I give you a little bit of insight. That's what I have, right? So you probably have to talk to these guys where this quantity come from. I think this quantity come from the Charles thesis, right? He works I don't know exactly how he come up with this, but it works because on ellipsoid it is a constant. So you hit with maximum principles. You can prove the Sutherland term is wrong. Also, you get a new proof for the ellipsoid case. So maybe I just quit here. Thank you. Non-trivial example of the solitons for alpha small, yes.
Oh, but for this Gauss computer flow,
No, for alpha small, yes.
already?
Yeah, we couldn't do anything for alpha small. Because alpha small, it's very tricky business. So alpha small, first of all, soliton, the limit may not be unique.
So what kind of examples?
The examples are examples with symmetries.
Yeah.
So Ben Angels construct lots of examples. For curve cases, he has complete understanding of it. So even our theorem fails. So you don't have smooth convergence to unique solitons. That's no more.
That's more like what I mentioned, 3 or 4.
His construction is mostly for curve. He completely understood the curve case. And for high dimensions, he has some constructions with symmetries. So if you have geometric symmetries, he could construct some examples for small alphas.
So what about slightly below the critical affine exposure?
I don't know. Slide is below the critical ones.
Yeah, because right now, right, you have affine one, the ellipsoid, you have the spheres, and are there any further gaps in some sense? Right?
Any gaps?
Yeah.
I don't know. So it's conjectured for alpha smaller than 1 over n plus 2, you don't get a smooth convergence.